All right, so this video is going to focus on acids and bases, and specifically it is for an organic chemistry course. And in this first part, we're going to look at the four factors that affect acid strength. Those are going to be the element effect, the inductive effect, resonance, and hybridization. And then we'll use those factors to rank acids according to their strength, where we'll first draw out the conjugate bases, and then we'll use those four effects to compare the strengths. And so before we get into ranking acids, let's first discuss these four effects. So the first one is going to be the element effect. And for this one, there are two separate rules that you have to follow. The first is that across a row, the acidity of an acid increases. And I'll use Ha to represent the acid. And this is because the electronegativity of the element A increases. And so we can draw out an example of this in a second. And so what this would look like is that a hydrogen bonded to a carbon is going to be less acidic than a hydrogen bonded to a nitrogen, which is going to be less acidic than a hydrogen bonded to an oxygen. And then fluorine would obviously be the most acidic here. And so it's important to note that at any given time, we always have all of these effects are going to be playing a role. And so we use the element effect when all other things are equal. And so here we can see that all of these are just normal hydrogens bonded to the element. And if we think about the periodic table, and I'll just do a quick sketch of the periodic table here, we know that electronegativity increases to the right here. All right, so that's the first part of the element effect. The second part is that down a column, the acidity increases for HA because A increases in size. And this is important because the conjugate base, or A minus, is able to stabilize that negative charge better than a smaller element would. And so for this, we could compare HF to HCl. So HCl is down the column. Bromine is even lower than chlorine. And so the most acidic one ends up being HI. And I'm going to modify this periodic table to now include the comparison down the column as such. All right. And so to understand why the element effect is use or why it ends up affecting the stability of or the acidity of the acid is because both of these effects stabilize the conjugate base. And so let's say that we have an acid like this, where when we deprotonate, if we have an acid-base reaction, we react this with some base, we end up forming this conjugate base, or CB. And so based off of the element effect, we know that this nitrogen would be more okay with having this negative charge than a carbon would be. And so based off of the element effect, this conjugate base would be more stable than a base that has or an acid that has a hydrogen bonded to a carbon. And again, we'll go through a few examples of like directly comparing some acids in a little bit. But again, the focus is on this conjugate base and how these factors that I drew out over here affect the stability of this conjugate base. All right, the next one we're going to talk about is the inductive effect. And so for the inductive effect, we care about the presence of electronegative atoms that are not directly bonded to the hydrogen. And so in words, the inductive effect is the pull of electron density through sigma bonds. And so the inductive effect comes into play when we have electronegative atoms that are removed from where the acidic hydrogen is. So let's take a look at this example here. And so we can see that the acidic hydrogen is right here. So it's not directly bonded to those fluorines. However, when it becomes deprotonated, we end up having this conjugate base. So I'll label this as conjugate base, and this is a starting acid. And so we can see that this negative charge right here is stabilized by these fluorine atoms because those fluorine atoms pull electron density through the sigma bonds through the inductive effect. And so because this conjugate base is more stable, that makes the initial acid more acidic. And so this effect is dependent on two separate factors, the proximity of the electron withdrawing group. So the closer that electron withdrawing group is to the conjugate base, the stronger it'll be. And then also the electronegativity of the atom itself. And one common question I get is how do you differentiate between the inductive effect and the element effect? And the way that you differentiate this two is whether the hydrogen is directly bonded to the atom itself or not. So in this top one, in each of these examples, the hydrogen was directly bonded to the atom that we're comparing through the element effect, as opposed to here, the group that we're using to for the inductive effect is removed from what the hydrogen is bonded to. And so for this last part of where the effect is stronger, if the atom or the electron withdrawing group is more electronegative, for that, something like fluorine would be better than having a chlorine. All right, the next effect that we're going to talk about is resonance. And this strengthens the acidity of an acid when the conjugate base can be stabilized through resonance structures. And I'll show an example of that in a second. And this is why it's really useful to also draw out the conjugate bases of all the acids that you're given, because you can compare the different resonance structures that each acid would get. So let's compare this acid versus a carboxylic acid. So here are our starting acids. And then what we can do is draw out the conjugate bases, where we deprotonate those acids. So for each one, I'm just pulling off that hydrogen and giving it a negative charge to the oxygen. And so now we can use resonance to compare which of these acids would be stronger. And so what we can see is that this one cannot participate in resonance. There's no way to distribute that negative charge across the molecule because there's no double bonds, there's no available conjugated systems where that negative charge can be distributed. And so because of that, we have no stabilization. That oxygen is fully carrying that negative charge in isolation. However, on the one on the right, we can see that this can actually participate in resonance with that carbon-oxygen double bond. We could show this resonance structure here, where we end up moving that negative charge to the other oxygen. And if you haven't done so already, I recommend reviewing that resonance video that I posted on how to identify resonance systems and draw them out. All right, and so here we can see that this one here is stabilized. And so what that means is that the conjugate base is more stable. And if it's more stable, that means the initial acid is more acidic. And because it's more acidic, that means it's more willing to give up that hydrogen and form that conjugate base that's more stable. And so all together from here, if we go back to that first line, we can identify that that second one as more acidic because its conjugate base is capable of engaging in resonance. All right, let's do this last one. So this would be the hybridization effect. And for this one, I'll show a few examples really quickly, or in a second, but first I'll write it down in words. And so for this one, the higher the percentage of S character in the conjugate base, the stronger the acid. And so basically for this, we can just compare different types of double bonds, or the number of double bonds that or triple bonds that a molecule has. So let's draw out these examples here. So let's say we have an alkane and we compare it with an alkene. And then we can do a triple bond here at the end too. And so here, the ones with more S character would be stronger. So here we can see that the conjugate bases, if we were to draw out all the conjugate bases for all of these, we would see that in this first one, we would have a negative charge on an sp3 hybridized carbon. On the second one, we would have a negative charge on a sp2 hybridized carbon. And then this last one, we would have a carbon or a negative charge on a sp hybridized carbon. And so since it's sp hybridized, we have 50% S character. As opposed to this middle one, here we have sp2, which is about 33% S character. And then 25% S character here, because it's sp3 hybridized. And so you can see that as we increase the amount or percentage of S character, it becomes stronger. And again, this only matters if the hydrogen is directly bonded to that double bond or triple bond. If you have that single bond or double bond removed from where that acidic hydrogen would be, it would have a minimal impact on the stability of the conjugate base. All right, so let's do a few quick practice questions to compare the different acidities using these four effects. So let's rank all of these in order of increasing acidity. So I'll just draw out some compounds here. And so these are going to be our starting acids. And so based off of the steps that we discussed up here, our first step is to draw out those conjugate bases. So we're going to identify the most acidic hydrogen on all of these. So we have this hydrogen right here on this first one. So we'll replace that hydrogen with a negative charge. In this next one, the most acidic one would be the one bonded to this oxygen. And then we have the one bonded to the nitrogen. And so those are our conjugate bases. And so we can see that the main thing that's really affecting the difference across all of these is going to be the element effect. Because in the first case, we have one that's bonded to a carbon, or the hydrogen's bonded to carbon, the next is bonded to oxygen, and so on. And so the only effect that we care about here is going to be the element effect, because the hydrogens are bonded to different elements. And so based off of our rules for the element effect, we know that the acidity of H8 increases across a row. And so since oxygen, nitrogen, hydrogen are on the same row, we know that the one that's bound to the oxygen, which is the furthest to the right on a periodic table, is going to be the most acidic. So it'll be a 3. Then that carbon is going to be least acidic because it's the one that's furthest to the right or to the left on the periodic table. Then that nitrogen is going to be in the middle. All right, we can next do a different set of acids. And here we will have multiple different effects. So let's do this one. This one. And this one. So these are going to be our acids that we have. And so for this one, again, the first thing we want to do is draw out our conjugate bases for each one. And so for that, we would deprotonate the most acidic hydrogen, which would be the ones bonded to the oxygen. And so from here, we can next look at which effects would be relevant to compare the stability of the different conjugate bases. And so out of our effects, we have the element effect, inductive effect, resonance, and hybridization. And so what we can see here is that all of these are bonded to an oxygen. And so we don't actually care about the element effect here because all of them, all the negative charges are on the same element. We're not comparing an oxygen versus a nitrogen like in this previous one. We do care about the inductive effect because we have this bromine in one of them. And so bromine, since it's electronegative, can pull electron density away and help stabilize it. And so through the inductive effect, this would stabilize the negative charge. Here we can also see that some of these are going to be stabilized through the resonance effect. And so for both this first one and this third one, we can draw out resonance structures that stabilize that structure. And so we can see that now we have differences for the first, second, and third one, where this first one is stabilized through two separate effects, and that middle one isn't stabilized through anything, and then that last one is stabilized only through resonance. And so now we can rank our order as this middle one being the weakest acid, or least like, or in other words, the least likely to become deprotonated. Then the second, the one on the end would be the intermediate because it's stabilized by the resonance, but not stabilized by the inductive effect. And then finally, this one on the left would be stabilized by both, so it's going to be the strongest acid. And so what you'll find with ranking acid questions is that a lot of times more than one effect is at play. It's a little bit tricky to compare the relative importance of the effects without like actually like experimentally determining the acidity of the different compounds. So in general, you won't see like you won't have practice. Usually, most classes won't have practice examples that contradict itself. If you do end up having a case like that, I would suggest prioritizing resonance and the element effect over anything else. Um, especially the inductive effect tends to be a little bit less important in comparison to those two. But for the most part, most classes don't try to challenge you by having like contradicting effects. All right. I'll also be posting a video that goes through acids and bases practice problems. And so this one, part one, will focus on ranking acids using these different effects, and then working on drawing out the conjugate bases and then using those conjugate bases to rank the acidity of different acids. It also has a question about how to use resonance structures to explore how they stabilize the conjugate base.